Hello, I welcome you once again to my channel. It is still your tutor Peter Ekaja, and today I'm going to be taking you through the integrals of exponential functions. Just a reminder, by the way, in case you need one-on-one tutoring services from wherever you are, from whatever part of the world you are, we do that perfectly at a very affordable price. And therefore, you can contact me using any of my contacts that I've displayed here. And in case you also need to find out more about us, you can visit peterekaja.com, and that is our website where we do more of the interactions with our learners. We upload more of the materials for them to benefit from, and you will see yourself through. You will see your learner or your daughter, son guided well with all the basics that he or she needs to be a successful mathematician. Now, without wasting a lot of time, let's get back to the point. We are here to see how we can integrate exponential functions. To begin with, I want to begin with integrals, particularly of this form. If I have an integral of the form exponential f of x with respect to x, for me to integrate this integral, I must just know that the result will be exponential of f of x, but I divide everything by the derivative of our power, which was originally f of x. So when you differentiate f of x, you write this very expression, divide by that derivative, and that becomes your result for the integral. Giving a few examples. For example, if I said I have an integral of exponential x with respect to x, this basically means I'm supposed to differentiate the power, which is x. That gives me a 1, and therefore the answer here would be exponential x divided by 1 plus a constant, and definitely this comes to exponential x plus a constant. So this is quite unique. We have now realized that when you integrate exponential x with respect to x, you get the same function. Just like we had talked about this earlier, that when you differentiate exponential x, you get the same exponential x. However, this only happens because we just have x as a power. What if we had expression like integral of exponential 2x with respect to x? Now here what you do, still follow the idea of differentiating the power. Get 2x, differentiate it. So your result will be exponential of 2x but divided by 2 and then plus a constant. That means even if I had an example of this kind, integral of exponential, let's say 3x minus 2 with respect to x, then I can directly tell the integral of this as exponential of 3x minus 2. I go ahead, differentiate 3x minus 2. Definitely the answer is 3. So I divide the whole of this by 3, and that will be plus a constant of integration. Now, this is the basic introduction I can give you on this. And now we are going to look at expressions that would actually require some other technique, but we shall build up the two techniques with the basics I've just introduced here to come up to our results. So let's move on quickly and look at the examples. Let's begin right away with this first example. We are integrating 2x exponential x squared with respect to x. So what do you do here? The best option is to make a very special observation and realize that when I let u to be, for example, x squared, which is our power here, differentiate it, it will give us 2x. So the best option would be let u to be x squared. Get your du dx. Du dx will definitely be 2x. Make dx the subject. Dx becomes du out of 2x. Do the substitution. When you do the substitution, now integral of 2x exponential x squared with the respect to x would now be the same as integral of 2x exponential u. But remember the x is already the u out of 2x. So we shall say the u out of 2x. Now you will realize that the variable will completely change from x to u because the 2x cancels with the 2x. And therefore, we remain with integral of exponential u du. And we said if you're integrating a function of this form, differentiate u with respect to u, that will definitely be 1. That means the integral of this will actually be exponential u plus a constant. Make a clear conclusion now and say integral of 2x exponential x squared with respect to x will definitely be exponential of x squared, because remember we committed ourselves and called u to be x squared. Then we realize it will be plus a constant of integration. So that will be our result for that particular question. Let's move on to example 2 and also explore more examples at a later stage. Okay, example 2 says we find the integral of x squared exponential of 2x cubed with respect to x. So what basically we do here? We shall say we let u to be. The best option would be letting u to be 2x cubed. So when I let 2x cubed to be u, differentiate it, the u dx would be 6x squared. Now the good news here, here is that we have realized that actually when I differentiated the 2x cubed, I got 6x squared. The x squared is actually going to help us cancel the x squared here after making dx the subject. So dx would now be du out of 6x squared. So from there, we can now say integral of x squared exponential to x cubed with respect to x is now going to be integral of x squared exponential to x cubed now becomes exponential u because our 2x cubed became u. Then dx becomes du out of 6x squared. Definitely we can see that x squared can cancel with x squared. That means we have 1 over 6, which is a constant, can come out of the integral sign, exponential u with the respect to u. Then when you integrate exponential u, we said you get the same function. So it will be a sixth e power u plus a constant. Then make a very clear conclusion and say integral of x squared exponential to x cubed dx is now definitely going to be 1 over 6 exponential, but our u, remember, is 2x cubed, and then plus a constant of integration. This is how simple it is to integrate functions of this kind, but the most important thing is to be able to easily tell what is the best substitution you can make. So let's move on to question 3. Okay, question 3 now brings in some kind of trigonometry. We are finding the integral of exponential tan x divided by cos squared x with respect to x. The simplest fact that we can go by here is by realizing first that we can rewrite this expression as exponential tan x, and then we realize that here we have 1 over cos squared x, which is the same as sec squared x, and then all this with respect to x. Now, the good news is that when you let u to be tan x, you differentiate it to give you sec squared x. So then definitely it makes the best substitution to be letting u to be tan of x. If u is tan of x, then the u dx is definitely going to be sec squared of x. And then from here, we make the x the subject. Make the x the subject, so the x becomes the u out of sec squared of x. Then after that, we go and make a substitution. So we shall now say integral of sec squared x exponential tan x with respect to x is equals to integral of sec squared x exponential u, because we called u to be tan x, the x becomes the u out of sec squared x. Clearly, we can see that sec squared can cancel with sec squared. That means we remain with integral of e power u with respect to u. That means when you integrate that, you still get the same very function and then plus a constant of integration. So our conclusion therefore becomes integral of exponential tan x, where we started from, divided by cos squared of x dx is actually the same as exponential of tan x plus a constant of integration. That is an arbitrary constant. I don't know how you find this, but I feel it's really some easy stuff, and that means we can now summarize with question 4. Let's look at question 4. There we are. Question 4 says we find integral of exponential cot x divided by sine squared of x with respect to x. It is almost a similar case like the previous question, to realize first that this can actually be modified to integral of exponential cot x, realizing that there is a 1 silent here over sine squared, which is actually cosec squared of x. So that means we are integrating cosec squared x exponential cot x. And then from that point, we definitely make the right choice, which is going to be letting u to be cot of x. If u is cot of x, then it means du dx becomes negative cosec squared of x. And then we make dx the subject, dx becomes du out of negative cosec squared of x. Therefore, from that point, we go back and make our substitution. We say integral of exponential cot x out of sine squared x, which we already said is the same as this very integral here, is going to be integral of cosec squared of x, and then exponential, where there is cot x, remember this time round, shall put there u, and where there is dx, we shall put the u out of negative cosec squared of x. Now we can feel free by pulling out the negative outside the integral sign, but guard it jealously. So we shall have integral of e power u with respect to u, but with a negative outside. So at the end of the day, you get negative exponential u plus a constant, but then you redefine what u is. So in our conclusion, we shall say integral of exponential of cot x out of sine squared of x with the respect to x is definitely going to be negative exponential of u, but our u is actually cot of x, and then plus an arbitrary constant of integration. So this brings us to about 4 examples now, and I really believe any good student, any serious student out there can now be able to try out some questions. So the next is going to be a simple exercise for you to try out. Please do so. In case you find a challenge, you can contact me through any of the options I gave you. Okay, so we can try out these few questions. Please do them. Practice makes perfect. And in case of any challenge, please, I'm always there at your service. I want to remind you again that please, if you've liked this, please subscribe to our channel, share with your friends out there, encourage them to do the same. And after subscribing, make sure you turn on the notification button so that you're always updated when we upload new content. I want to say bye-bye to you and see you again in our next video.